I just had the demoralizing experience of making this entire screencast and then realizing that it wasn't recording. And I had that experience earlier with the AP one, except it wasn't recording my voice. So, that's rough. Okay, here we go. Allotropes are when you have two different forms of something that are effectively the same element but have different structures, which cause it to have different properties. The two most obvious examples are diamond and graphite, which are both pure carbon and are so completely different. So diamond is just unbelievably hard. It does not conduct electricity. It's transparent and reflects light in a certain way. And graphite, conversely, these are both showing graphite. This one just from different angles, is made of these sheets. It's like really slippery. Like you can, when you use your pencil, you're basically like sheets of it are like coming off onto your paper. It conducts electricity. It has a low melting point. Black, it's just a totally different thing. So you can see here diamond and graphite. There's other elements that also do that, and it is purely a function of the bonding on an atomic level, which is pretty great. So diamond structure, if you guys can see here, every carbon is bonded to 4 other carbons, and it that causes it to have like a really rigid structure, whereas graphite has these sheets. Okay, another one that does that is sulfur. This one looks like these little flakes, and this one's more chunky. They just have different properties because of different bonding. Phosphorus is another one that does that, white, red, and black, and there's other kinds also. Okay. What you need to know is what an allotrope is. So we might say that diamond is an allotrope of carbon, for example. Buckyballs, all these different things that have physiological benefits. Carbon allotropes can be used for that kind of thing too. My husband just walked in and probably knows a million times more things about than I do. Okay. All right, so you would maybe, for example, sulfur would have different actual formulas, but for something like diamond and graphite, because there's not like a unit of it that repeats, you would literally write carbon, solid, comma, graphite, or carbon, solid, comma, diamond. Like an AP next year, we would do that. Okay. This was a big slide, so what did we do? All right. So we're going to do a phase diagram, which is shows what phase a substance will be in under different temperature and pressure conditions. As always, we will be using H2O, and the x-axis here is going to represent temperature, and we're going to do it in degrees Celsius because that will be easier to relate to, and our y-axis here is going to represent pressure. And we're going to do that in atmospheres because atmospheres are easy. If you have, if you have 1 atmosphere of pressure, that is like basic normal pressure, basically. So, for example, if you are in Los Altos on a regular day, the pressure is probably about 1 atmosphere. Okay, so, okay, let's think about what state of matter water would be in under different conditions. So let's imagine that you have, wow, that was bad. Okay. Let's imagine that you have a really high temp and a really low pressure. So what state of matter would you expect water to be in under those conditions? High temperature and low pressure. So think about that for a second. Okay. Super high temp, super low pressure, of course. Water will be in its gas form. There's basically nothing holding the particles together. There's no pressure, and they're so hot that they're moving super fast, and their IMFs just don't exist. Okay, conversely, super low temp and super high pressure, what would you expect its state of matter to be? Okay, solid, so everything in between is a liquid, but how do they all relate to each other? With these lines that I will show you. So we have something that comes up from here, and then it goes with a negative slope that way. It's a very slight negative slope, and this kind of curves up like this and reaches this weird little point. And we've got these doodads going up and over. Okay, so you can see that under these different conditions, water will have different states of matter. H2O will have different states of matter. So let's imagine that 1 atmosphere is right here. Okay, so I want you to think about if 1 atmosphere for H2O is at that point on the y-axis, then what temperature would this point here correspond to? Okay, 0 degrees. If that's what you got, good job. I don't have to write the Celsius part. Okay, because it's the point at which water transitions from a solid to a liquid, or conversely, from a liquid to a solid. So that might help you with understanding what temperature this would be at. Make it a little lower. Okay, what temperature would that take place at? The transition from liquid to gas for water will happen at 100 degrees, although we know that that's the normal boiling point, right? Okay, there is this weird section up here that we won't really talk about very much. If you would have enough pressure and enough kinetic energy, the transition, like the boundary between liquid and gas, sort of disappears, and you have what's called a supercritical fluid. Fluid is actually a term that encompasses both liquids and gases. And it's so hot that it's like a gas, and the pressure is so high that the particles are close enough together that it's like a liquid. I've shown a demo of that before, and it's a little bit underwhelming. You're welcome to go look for it on YouTube, but basically they have this like little window, and they have, I can't remember if they use water or CO2. It might be CO2, but they basically have like the liquid version in the bottom, and then they have the gas version in the top, and then it starts to vibrate, and then you kind of like squint at it, and after a while this line just sort of disappears, and it all just looks kind of cloudy, and that's it. So knock yourself out if that interests you. The point is that it is like both, and I do believe that there are applications of that are useful, but I'm not very familiar with them. This point where that transition happens is called the critical point. Okay. You'll also notice down here, this is called the triple point. And this is a stage at which all 3 states of matter can exist in equilibrium, actually. Okay, so you would have basically like, I was going to do this for you at school also, actually. The trick to it is that because 1 atmosphere is up here and the triple point is down here, it's actually at something like 0.006 atm. You have to basically put it in a vacuum, and it has to be super close to 0 degrees. So you put super cold ice water into a vacuum, lower the pressure so much, it actually will start to boil. And if you do it right, you can see ice forming while the boiling is taking place. It's pretty fascinating. And then when you take it out, it's cold. It's close to 0, but there was boiling. Okay, let's talk about phase changes. The phase change from a liquid to a gas would be called vaporization. If you said boiling, that is understandable, but vaporization is a little bit more general. Okay, another one that requires an increase in temperature. So I'm drawing these arrows from left to right, which means it represents an increase in temperature on the x-axis. Okay. From a solid to a gas, you may not know what that's called, but you may. Sublimation. Can you think of a solid that does that? Okay, CO2, dry ice. It's called dry ice because it doesn't exist as a liquid at atmospheric pressure. So the difference between CO2 and water, well, one difference is that its triple point is at like 5 atmospheres. So when we're at 1 atmosphere, we're all the way down here, and it just goes straight from solid. There's no liquid state at all at that point. Okay. Lastly, solid to liquid is, of course, melting. And I'm drawing these all in red because you have to heat something up to get that change to happen. Okay, conversely, green doesn't really make sense for the opposite, but whatever. Okay, what is it called when something goes from a gas to a liquid? What do you think? Condensation. That would be like water condensing on the side of a soda can. Okay, I don't know why these arrows are so long. Okay, green, from gas to a solid. This is probably not familiar to you. Deposition. Okay, an example of that is frost. Frost is when water vapor in the air can actually deposit straight onto the grass as a solid, which it's probably a little bit confusing that would happen, because you would think the pressure would have to be this low for that to happen, but anyways, it does happen. It's not quite that straightforward. Okay. It's sort of similar to how like evaporation can happen below the boiling point. Anyways. Okay. And also actually deposit is what, when you like take old ice cream out of the freezer. Maybe some of you don't have the experience of ice cream sitting in your freezer for a long time. I don't have that experience, but people who do, maybe like your frozen vegetables, they get all that ice crusted on them. That's as a result of water vapor depositing onto the vegetables. My husband calls it freezer spice because it kind of has the smell of all the other stuff in the freezer. That's because there's been like an exchange of gas and water molecules between the things in your freezer as things are sublimating and depositing in there. Okay. All right. Lastly, melting and freezing. Freezing. Okay. The last point that I want to make about this graph, I will make later. I think that's all I wanted to say right now. Okay, let's look at CO2. Not so different, a little different. One thing you notice is that the triple point is at 5 atmospheres, which is why, again, at 1 atmosphere, it goes straight from solid to vapor. Okay, it has its own critical point, its own triple point. Another difference here is that this line here between solid and liquid has a positive slope, and we'll talk about why in a little bit. Okay, carbon and sulfur, they have multiple, they don't just have 3 states of matter, and that's because of allotropes. Okay, so we can see that graphite, to turn into diamond, you have to increase its pressure. So just to give you a sense of what 10 to the 9th pascals is, pascals is like kilopascals. So 10 to the 9th pascals is 10 to the, how many kilopascals? 6. Okay, which is a million kilopascals. And if there's 100 kilopascals in an atmosphere, this is 10,000 atmospheres. So just a lot of pressure, basically, is the point of that. And again, I think we've talked about this before. If you have a relative cremated, you can take their cremains. I don't know if you've heard that term before. It's like cremated remains becomes cremains. There's something sort of morbid about that and interesting. Okay, you can take their cremains, send them off somewhere, and they'll just put it under a lot of pressure, and it turns into diamonds, and then you can wear it around. So that's fun. Okay, this is what the states of matter are called, and I would like you to try to fill these out. Phase changes that require energy are endothermic. Endo means energy, in energy, okay? And there's other phase changes that energy goes out, like you have to make them colder, pull energy out of them to get them to happen. Oh, there's our frost, okay? And there's our pretty diagram for water. Oh, cute little teapot. All right, so let's talk then this last point here about, still going, this graph here. Why does this have a negative slope? Okay, it has to do with these two diagrams over here. Take a second and try to figure out what each of those are. Okay, this one is ice. You can tell because you have these little water molecules, and each of them is connected to 4 other water molecules. This other one's 4th one you can't see. Because in ice, each molecule does 4 hydrogen bonds. And in order to do that, it has to spread out a lot. Wow, that was bad. 4 hydrogen bonds, okay, spreads out, which means it has a low density. Okay, conversely, when you get enough energy in there, they start to move around, and some of these hydrogen bonds will break, and they kind of get more jammed together in water. So water, because of its higher kinetic energy, because of its higher temperature, some of the IMFs are overcome, and the hydrogen bonds break, and they get smashed together. Or they can be smashed together anyways. Okay, which means that it has higher density. I hope yours looks nicer than mine. Higher density. Okay? So why does that matter? Because let's say that you have a sample of ice and it's nice and solid. We can even, if it makes it less confusing, put it at 1 atmosphere. So you just have this ice and it's sitting at 1 atmosphere pressure and it's a tiny bit below its freezing point. And let's say you subject it to an immense amount of pressure at a constant temperature. So we're going to stay in the same place on the x-axis, but we're going to go up in pressure. So if we do that, we see the phase change that happens is, I'm just going to, okay, close enough. The phase, okay, is that straight up? Okay, the phase change that happens if you have a solid sample of water at 0 degrees or -1 degree Celsius at 1 atmosphere pressure. If you subject it to immense pressure, it becomes a liquid. Why? Because the liquid is more compressed than the solid version. So in response to all this pressure, the molecules get smushed together as much as they are able to be smushed, and that is basically what water is like in its liquid state. And that makes a lot of sense if you think about the ocean being like 8 miles deep or 6 miles deep, however it is, in the Atlantic. There's so much pressure above it that whatever water is at the bottom of all of that huge column of water is going to be as dense as water can possibly be, and that will be its liquid state. So if that wasn't true, then it would kind of make sense that at the bottom of oceans you would have solid water, which would do all sorts of weird things to life on Earth. So hopefully that makes sense on some level, but if you wanted to memorize like the takeaway, why does this line have a negative slope? It's because ice is less dense than water. So, subjected to high pressure, close to the freezing point or the melting point, solid will become liquid, or in other words, it will melt. Weird. I'm wondering and thinking about like that machine. I'm thinking about people talking about, never mind, ice skates, how they melt the ice. I think it's friction. Never mind. Okay. I think I'm pretty much done. I'm going to quickly look for a video of water's triple point. You can bail now if you'd like. But we'll just, or you can look on your own. Oh, there's your supercritical video. There's your supercritical fluids video. It's just that thing with the... Okay, we'll just do this one. Of 4x speed. That sounds good. Okay, so you can see there's ice in a tiny dish. This is all in a vacuum. That little hole at the bottom is where the air is being sucked out of the vacuum. Okay, you can see little bubbles forming. So you can see that it's starting to boil. I hope you can see new ice forming. Maybe you won't be able to. Regardless, the fact that it's boiling and the ice is still present is pretty cool. Oh, look at the new ice. Do you see that? Oh, I thought I saw it. Did I see it? Or is that just really aggressive boiling? Anyways, regardless, you can see. Oh no, it is. Oh my gosh, it's so cool. Look, there's ice all on the sides. You see that? It's like crusting over. On the far right side, you can see that there's like a layer of ice forming that wasn't there initially. Oh, it's so cool. I wish I could show you in person. Oh well. Wow, look at that whole layer of ice. Like the bubbles are getting stuck under it. Oh, it's crazy. So cool. Okay, I hope you stuck around for that. That was awesome. All right, get me out of here.